All right, so this is another one of those so-called analytic processes where we're going to start throwing everything that we got at a rational function in order to come up with, some certain features of it, certain points, so on and so forth. And we'll blend all that into the coordinate plane in order to come up with a sketch of those tougher rational functions. Now, here's a step-by-step process that we take in order to do that. Not every step applies. It'll just depend on what function you're given. But in some cases, every step does apply. In most cases, though, maybe one or two of these steps will not apply. So I'll go through the whole process, and we'll work on a couple of examples and get some practice with it. The first thing that you want to do is factor your rational function's fraction. In other words, you want to factor the top polynomial and bottom polynomial if possible. So for instance, we might be able to rewrite our rational function in a factored form where the top is, say, x plus a, x plus b, and on the bottom we've got x plus c, x plus d. Now this is just one way in which a rational function may factor. It won't always be in this format. There might just be a GCF. It might not factor at all, or there might be more than one or more than two factors on top or bottom. But regardless, the overall thing with step one is just to factor the numerator and denominator if possible. Now, as for the domain, what we want to do is include the set of all x values, or the set of all real numbers, excluding those that create division by 0. Okay, in this case, if we look at the bottom two factors, the first one, x plus c, okay, negative c would create division by 0 in that case. So I'll say x cannot equal negative c, and then negative d would create division by 0 in that second factor. Long story short is exclude values of x that cause division by 0. In some rare instances, your rational function might simplify. So let's say that we factor both top and bottom. Let's say the top is still x plus a, x plus b, but on bottom, let's say we have x plus a showing up again along with x plus c. So if we have a factor on top that literally looks the exact same as a factor on bottom, this rational function would simplify to whatever remains on top and whatever remains on bottom. Now, anytime you have factors that simplify in this way, you're going to get what's called a hole in the graph, which when we plot a hole, it looks like an open circle. So you might have one branch of your rational function coming down like this, but based on the value of x that would make the two factors 0, we'd be able to identify there being an open circle in the graph where the graph comes up to that open circle, kind of skips it, and then continues on with the rest of its journey. Now to find a hole, here's what we do. We take this factor that cancels, and we set it equal to 0. And then we solve for x. And this would tell us the x coordinate of the hole. So right underneath this open circle in our diagram, let's put negative a. And then what we do is we plug that negative a back into our reduced version of the rational function. To get negative a plus b on top and negative a plus c on the bottom. And then we simplify that. And then whatever value this simplifies to, that's going to be the y-coordinate of the whole. So I'm going to call that r of negative a. And just bear in mind that the version of the rational function r that we use is the reduced version. And by the way, I did not include examples where we have a hole here, but I will upload kind of like a supplemental video. But I usually don't put rational functions with holes on like exams or anything like that. But it is good to be aware of them. So if none of our factors cancel, then we move on to step 3, where we find the vertical asymptotes. And let me remind you that in order to find the VAs, what we have to do is set the denominator equal to 0 and solve for x. So I'll say denominator equal to 0 and solve. And remember, these are going to be like those vertical dashed lines that we were sketching back in section 5.5. Okay, so depending on how many factors you have in the denominator, that's going to dictate how many vertical asymptotes you have. All right, so if we have 2 factors in the denominator that remain after we simplify, then we're going to have 2 vertical asymptotes. So on and so forth. For horizontal or oblique asymptotes, what we have to do is compare degrees. And usually what you do is you use the standard form version of the rational function. Now, back in the last section, the numerator polynomial was generically defined as a sub n x to the n plus yada yada. And on the bottom, that polynomial was b sub m x to the m plus yada yada. And what I mean by compare degrees is look at the highest power in both the top and the bottom. And you may recall that there were 3 cases. In the case where the degree on top was smaller than the degree on bottom, by default, the horizontal asymptote was the x-axis, which had the equation y equals 0. And we were calling this case 1. If the powers equal each other, then the horizontal asymptote was the ratio of the leading coefficients. Let's say that ratio is positive, then we'd have our horizontal asymptote a little bit elevated, and the equation for it would be a sub n over b sub m. And that was case 2. Last but not least, we could have the degree of the top larger than the degree of the bottom, in which case we would get a so-called oblique asymptote. And one example of an oblique asymptote would be a line that has a positive slope, such as this. And you may recall that the equation for the oblique asymptote was the quotient polynomial that we would get after we do long division, and that would be case 3. So far, so good? We're going to tie in finding x and y intercepts if possible. To find the x-intercepts, give you a shortcut here. What we do is we set the numerator of our factored rational function equal to 0 and solve. Okay, and for a y-intercept, we plug 0 into the rational function. So by doing r of 0, we would figure out where our graph crosses the y-axis. And then by setting our numerator equal to 0, we would be able to figure out where the graph crosses the x-axis. And then last but not least, we graph the rational function using a graphing calculator. And here's a tip as to how we'll want to enter our rational functions into the graphing calculator. You want to surround the numerator in parentheses. So let's say that the numerator is indicated by p of x, which is a polynomial. So this extra set of parentheses is critical. And then our division bar, which will be slanted in the calculator, and then an extra set of parentheses around the denominator. And last but not least, there are going to be two versions of our rational function. I find it easier to use the standard form version. That way there aren't so many parentheses crowding the place. You guys ready to do this? All right, so I know it seems like a lot, but over the years of teaching this section, I find that after just a couple of examples, a lot of it becomes routine. It's quite magical. Here we go. Our first example. Analyze the graph of r of x and use the information to sketch the function. Let me double check something. Okay, yeah. All right, first thing we're going to want to do is factor the top and bottom. So let's look at the numerator polynomial. It has a leading coefficient of 1. So we'd want to figure out factors of negative 12 that add up to positive 1. And those would be positive 4 and negative 3. So that's how the top factors. And then how does the denominator factor? Yep, the denominator is difference of 2 squares, so x plus 2 times x minus 2. So that's our factored version of the rational function. My question for you is, do any of the factors on the top cancel out with those in the bottom? No. So because of that, there's going to be no whole. So you'll notice at the very bottom of the page, we have our coordinate plane, but we also have like this little list. And where it says whole, because none of our factors cancel, we can put none. So no whole. Let's see if this thing has any vertical asymptotes. And the strategy for finding vertical asymptotes is to set the denominator equal to 0 and solve for x. Now you'll want to use the factored form version because it's a little quicker to solve for x that way. And by setting each factor equal to 0 and solving for x, we'd see that this graph is going to have two vertical asymptotes. Okay, so negative 2 and positive 2. So let's go back down to our list. And where it says VAs, let's write x equals negative 2, x equals positive 2. And before I go back up to include more work, you may recall that there's a strong connection between vertical asymptotes and domain. Vertical asymptotes are where division by 0 occurs. So with regard to domain, these are exactly the values of x that we would not want to plug into our function. So once you have your VAs, you can quickly get your domain by writing out set notation and being sure to exclude those two as values of x to plug in. Does that make sense? Now for a horizontal asymptote, we have to compare the degrees. And the easiest way to compare the degrees is to look at the original version of the rational function. The highest power on top is 2, and the highest power on bottom is 2 as well. In other words, the numerator has a degree of 2, and so does the denominator. So this is a situation where n equals m. Does anybody remember what case that was from the last section? It's case 2. Now case 2 says that the horizontal asymptote is going to be the ratio of leading coefficients. In other words, a fraction, in which case the numerator is 1 and the denominator is 1 as well. Now before I go back up, it's only possible to land in one of those three cases when analyzing whether or not a graph has a horizontal asymptote. So because we have case 2, it's not possible to have case 1, and it's also not possible to have case 3, which tells us that there would be an oblique asymptote. So because we have case 2, it means that there's going to be no oblique asymptote. So let's write the word none again.
Question for you.
Yep.
Where'd you get the 1 over 1 or y equals?
Yep, it came from the ratio of leading coefficients.
Gotcha. Got it.
No problem. So there's no oblique asymptote. That would be a case 3 situation. So let's move on to see if this thing has any x-intercepts. And the shortcut for that is to set your numerator equal to 0. And the factored form version of the numerator would be easier to use because it's quicker to solve for x with it. How many x-intercepts would this graph have? It would have 2 of them. One of the x-intercepts would be at -4. The other would be at x equals 3. I'm going to write those as ordered pairs just so that we don't confuse them with vertical asymptotes. And then the y-intercept is found by plugging 0 into the rational function. Now, I've used the factored form version for a couple of these steps because the factored form version is easier to solve for x with. I find that with the y-intercept, the original version, in other words, the standard form version, is a little easier to use. It requires less arithmetic. If we plug it into the standard form version, the numerator gets a couple of terms that zero out, and the denominator gets a term that zeroes out. And this will lead us to -12 over -4, which gives us 3. So as an ordered pair, the y-intercept would be 0, 3. Now, although it's not included as a step on the first page, I believe my math lab will want this information within these types of problems. So there's a little space in order to do this with. And what they might want to know is whether or not this graph intersects the horizontal asymptote. So I'll make a little workspace for that. HA intersection. I'll put a question mark. Now, a graph will never cross a vertical asymptote, but as we're going to see with this example, it is possible for a graph to cross a horizontal asymptote. It won't always be the case. If you recall from the last time, we had rational function graphs that didn't cross the horizontal or the vertical. But with these tougher rational functions, there tend to be certain scenarios where just by design, with the numbers and stuff, that the graph will cross a horizontal asymptote. So that information isn't as critical, but is still nice to have. Now, to see whether or not this crosses the horizontal asymptote, what we're going to do is set our standard form version of the rational function equal to the value of our horizontal asymptote, which is 1. And we're going to solve for x. To start solving for x, we're going to want to clear out the denominator of x squared minus 4. And we can do that by multiplying each side by x squared minus 4. And that gets us to x squared plus x minus 12 equaling x squared minus 4. What do you notice that's going to happen with the x squared terms? They're going to cancel. Yep. So if we subtract x squared from each side, they cancel, and we're left with x minus 12 equals negative 4. And by adding 12 over, you would see that there is going to be an intersection between the graph and the horizontal asymptote because we got an answer for x. And the point at which our graph is going to cross the horizontal asymptote will have an x coordinate of 8. And what do you think the y coordinate might be? Well, keep in mind what we set it equal to. We set the equation equal to 1. So it's going to have the same y coordinate as the equation for the horizontal line. And that's about all we can gather by hand. Let's start transferring this information into the coordinate plane. Going from top to bottom, first piece of information we can sketch out is the vertical asymptotes. So these vertical asymptotes, vertical dashed lines, they're going to cross the x-axis at -2 and +2. We also have a horizontal asymptote, which is going to cross the y-axis at y equals 1. Two x-intercepts, one at -4, 0, the other at 3, 0. One y-intercept at 0, 3. And then, based on our recent work, our graph is going to intersect the horizontal asymptote at 8, 1. And although that's a lot of information, it's still not quite enough to figure out what the branches of the graph will be doing. You can probably guess that there's going to be 3 pieces to the graph because we have 2 vertical asymptotes, but how we connect them through these points is still somewhat of a mystery at this stage. So that's why one of the very last things in that list of steps on the last page is to graph it in the graphing calculator. All right, so with that said, we'll go to our graphing calculators, and in Y1, we're going to enter the standard form version of this function. So that's going to be x squared plus x minus 12 in parentheses on top, and then x squared minus 4 in parentheses on bottom. Where's my graphing calculator? Okay, so let's go to y equals, in parentheses, x squared plus x minus 12, fraction bar, denominator, x squared minus 4. And if you have a TI-83, don't panic. After we press Zoom 6, I'm going to show you a workaround to it. Okay. If you have a TI-84, let's all press Zoom 6. And if you have a TI-84, you'll notice that we get 3 disconnected pieces. And so there are 3 branches to our tougher rational function. TI-83 folk, are you seeing a little bit of a different picture? So if you have a TI-83, you're probably seeing your calculator attempting to connect all 3 pieces together. Can I get confirmation on anybody that might be seeing that? Okay. So if you have a TI-83, the way around that is to press the zoom and select option 4 where it says zoom decimal. Now granted, it's going to take you a little bit closer to the graph, but you should be seeing it a little disconnected now. Now if you want to go a little bit higher in the coordinate plane to see what that middle piece is doing, you can always adjust your window and maybe choose a Y max of, and let's see what 8 does. Okay, so Kevin, are you seeing your pieces disconnected now after you did Zoom 4? All right, cool. I'm going to go back to my Zoom 6. And if we go from left to right, the first 2 pieces are disconnected by that vertical asymptote. And you can see how the top and bottom portion of these branches kind of straighten out somewhat like a vertical line. And that's also happening between the disconnect of the middle and last piece as well. The top part is going up to positive infinity, bottom part going down to negative infinity. And then the outsides of the graph kind of flatten out a little bit. And the reason for that is because of the horizontal asymptote. Now, unfortunately, the calculator will not draw in those vertical dashed lines or horizontal lines, which is why we do the by hand stuff. It's part of the reason why we do it by hand. But you can see that there's evidence of those asymptotes on the graph here, as well as, we can verify our x and y intercepts just by looking at the graph. So what we'll do is connect our points as best as we can to resemble what our calculator is showing us, and then that'll be it. So I'm going to start with the piece on the left. I'm going to start at the x-intercept, and if I go to the right, the vertical asymptote turns it down to negative infinity. And if I go to the left, I'm going to approach the horizontal asymptote, but I'm going to stay underneath it. And the reason for that is because there's only one point of intersection between the graph and the horizontal asymptote, and that's at 8, 1. Now I'm going to go to the y-intercept, and if I go to the left of it, we saw that middle piece of the graph shooting up to positive infinity, as well as when you move to the right of it. But be sure to never cross or touch these vertical asymptotes. The graph will never do that. And then with our second x-intercept, if I go to the left of it, we're going to turn down and approach the vertical. And then to the right of this x-intercept, we're going to go to the right and cross the horizontal asymptote at 8, 1, and then just go a little bit past it and put our arrowhead. And there's our graph. You know what it kind of reminds me of? Let's see if I can draw it. It's the first time I've ever tried drawing it. Ta-da! Yep, it looks like a. They always get me too. It kind of reminds me of a Piranha Plant. Uh, my son and I were playing some Smash Bros yesterday, and I always choose just a random selected character, and this was one of them. So, oh, thanks, Owen. I'm just kind of doing this off the cuff. So anyway, that's what the graph kind of reminded me of. All right, folks, you guys have any questions about this example? I know it's kind of a long one, but man, we threw a lot of math at it. Okay. I'm going to get you guys started with this one and then give you guys some time to see if you can maybe clinch the entire thing, and then we'll go over it and we'll have our break. So we're going to do a very similar process. Different rational function this time. We'll start by factoring. Now the numerator is just x. There's no factoring to do with that. But the denominator would factor as x plus 2 times x minus 1. Now, do any of the factors in the bottom cancel out with x? No. So where it says whole, you can put none. You'll then want to move on to find the VAs. My tip for you there is to set the denominator equal to 0 and solve. Then the HA, you'll compare degrees. You should land in either case 1 or case 2, so there's not going to be an oblique asymptote, in which case you then move on to x-intercepts. You set the numerator equal to 0, and then the y-intercept. Plug 0 into the function. And then we'll work on whether or not the graph intersects the horizontal asymptote when we go over the solution. But for now, let me see if I can have you complete these parts, translate that information into the coordinate plane, and then use your graphing calculator to get the rest of the graph. Right. I'll check in with you in about 5 minutes. All right, gang, let's go over that solution. All right, so the vertical asymptotes, I set the factored form version of the denominator equal to 0. We'll see that there are two VAs, -2 and +1. For the horizontal asymptote, oops, that's actually a mistake there. The degree of the numerator is 1, degree of the denominator is 2. This is a situation where n is less than m. There we go. And that's case 1, which tells us that the horizontal asymptote will be y equals 0 by default. In other words, the x-axis. If you set the numerator equal to 0 to find the x-intercepts, you solve the equation right away and get 0, 0 as the x-intercept. And by plugging 0 into the rational function, the standard form version, we get 0 as well. And so there's an overlap between the x and y intercept at the origin. Now, whether or not the graph intersects the horizontal asymptote, we'll do this together by setting the standard form version equal to the value of the horizontal asymptote, which is 0. And we'll clear out the denominator by multiplying each side by it. We get canceling on the left with x left over. And then 0 times anything is still 0. And so there is an intersection of the graph with the horizontal asymptote, and that would be at 0, which is our answer, and then 0, which is the value of the horizontal asymptote. So lots of things happening at the origin for us, it seems. And all of this information, with the exception of the intersection of the HA, is cataloged on this list over to the left. One thing I want to point out is just remember that the vertical asymptotes give way to the domain. Okay, so -2 and 1 are good for finding VAs, however, they're bad for the domain. So I exclude them at the very bottom. And this is all the information translated into the coordinate plane. We have our x and y intercept there, as well as the point of intersection of the graph with the horizontal asymptote. Yep, I set it to 0 because that's the value of our horizontal asymptote. No problem. And on the previous page, I set it equal to 1 for the same reason. So going back to this, we have the origin at which we have our x and y intercept, as well as the intersection of the graph with the horizontal asymptote. Our vertical asymptotes, -2 and +1. Of course, our HA, which is the x-axis. And then just a reminder to use the standard form version with both the numerator and denominator in parentheses in your graphing calculator. This is what my calculator showed with Zoom 6. If you have a TI-83, you want to do Zoom 4. And we can see evidence of the verticals and horizontal asymptote in the graphing calculator should you have graphed it. And one thing I want to point out is that I know that these ends of the graph are not going to cross the horizontal asymptote because according to our algebra, the only place where the graph crosses the horizontal asymptote is at the origin. Okay, so when we draw these branches, obviously, no crossing or intersecting the vertical asymptotes. But with regard to the horizontal asymptote, we're going to kind of flare the ends out and just make it look like we're going to hover along the x-axis without crossing or touching it. Questions, comments, concerns, winning lotto numbers? Did you guys get similar results to mine?